let us talk about the multiple reaction system in this particular lecture under the head of polymer reaction engineering. So, before we start, let us have a look about that what we studied previously. We discussed about the various performance equation attributed to the recycle reactor. Then we studied about the concept of autocatalytic reactor and their performance equation, and which is the best reactor scheme is suited for our optimized reaction system. Now, what we are going to study in this lecture, that is attributed to the multiple reaction system having the parallel, series, complex, independent type of system, and then we will have the discussion about the quantitative treatment of various product distribution, because this is again a very much important in case of a multiple product stream being generated in due course of time in a particular reactor system. So, let us have a discussion about the multiple reaction. Now, usually in a single reactor system or reaction system, the flow pattern within the vessel, sometimes it affects the performance or the size of the reactor, and there is a need of only one rate expression to describe its kinetic behavior. That is quite obvious, because there are certain mathematical tool which can accommodate only one rate expression. You cannot afford to have multiple rate equation because of the complexity of the nature. Now, in multiple reaction system, more than one reactions occur simultaneously. So, you need to take care of all those reaction system or reaction parallelly. Now, multiple reactions sometimes require more than one rate expression to describe its kinetic behavior, thus making the system more and more complicated in the nature. So, the reactor size, distribution of the product, they are sometimes affected by the flow pattern in the reactor, because see, there are multiple variables in those reactor system, and those multiple variable also affect the performance equation, also affects the rate expression. So, there are both desired and undesired type of a reaction. Sometimes you may interested, or sometimes you may not interested, and these reaction may take place during the course of the multiple reaction system simultaneously. So, when we talk about this particular concept, there is a requirement of a minimization of undesired side product, because it is quite obvious that if you are looking for the efficiency of the reactor system, if you are talking about the best conversion or a yield of a reaction system, then you have to take care of this particular undesired side products, and you have to curtail these things. So, the size of reactor sometimes again play a very vital role. Now, to maximize the desired product, sometimes you need to optimize the size of a reactor. Concentration terms, sometimes they are more convenient to deal with multiple reaction rather than the conversion terms, although you cannot nullify the effect of conversion in the multiple reaction system, but this for the dealing aspect or for the development of any mathematical equation, these concentration terms are more convenient to handle. Now, there are relative rates are involved in the analysis of reaction. Now, in this particular concept, we will study the determination of the reactor size, how we can deal with the product distribution concept. Now, these are things are quite essential, because ultimately they affect the separation process, they affect the various other allied processes in situ. Now, these type of multiple reactions sometimes can occur usually either by themselves or in pair or all together. So, there are various permutation combination or various classification or various types of multiple reactions like parallel reaction, series reaction, complex reactions, and sometimes independent reaction. So, let us start with the parallel reactions. In this type of reaction, reactant is usually consumed by two different reaction pathway to form different type of products. Now, these type of reactions are sometimes called as the competing reactions. Now, let us see about the chemical equations in which you can represent the parallel reaction system. Now, here if we are having one reactant, and this may participate in two aspects, this R, that is the desired product, and sometimes it may gives you the undesired one, side reaction, waste product, etc., undesired product. Now, it can be represented sometimes, if we wish to write in terms of reaction engineering concept, then it may be represented as like this. This one is the desired one, and it is undesired one. If we see that sometimes we need to write the corresponding rate equation for the formation of a desired product versus undesired product. So, we can write these equations like RR is equal to dCr upon dt Kr Ca A1. Now, you see here this is the rate equation for the desired one, and this is a concentration approach. So, this may be termed as the equation number 1. Now, sometimes we may look into the disappearance of a reactant A because it is being consumed in due course of time during the reaction, and usually it is the sum of the formation of the product R and S, usually represented by the rate equation. So, sometimes we can write this R S is equal to dCs upon dt Ks Ca. Now, this is equation number 2. Now, if we talk about the disappearance rate, then the rest equation can be represented as minus Ra R plus Rs. If we take the help of equation 1 and equation 2. So, in that case, we may write Ra is equal to Kr Ca A1 plus Ks Ca A2, that is equation number 3. Now, here the Ca, Cr, Cs, they are the concentrations of A, R and S usually represented in mole per liter. Similarly, Kr, Ks, the specific rate constants of desired product stream and undesired product stream, and small a and small a2 are the respective order of the formation of the reaction for desired one and undesired one. Now, let us talk about the series reactions. Now, when we go into the details of the series reaction, this type of reactions, the reactant is consumed to a product or produced an intermediate product sometimes which can react further to form another product. So, these reactions are also called the consecutive ones. Suppose you are having any reactant and then you are forming another product, this may be consumed over the period of time. These may be termed as the intermediate products. So, now here how you can represent mathematically. So, if we try to write these series reaction which can be represented as A, that is converted into R, and sometimes it may lead to form the undesired one, undesired product. So, this Kr, this is obviously desired one, and then this is Ks and this is the undesired product. Now, when we talk about the mathematical representation or when we talk about the rate equation for the decomposition of reactant A, then it can be represented as Ra is equal to minus dCr. Minus sign is quite obvious because the A is being consumed in due course of time, that is dCr upon dt minus Kr Ca A1, that is my equation number 4. Now, the rate of formation of intermediate R and the final may be the undesired product, but can be represented as Rr is equal to dCr upon dt, that is Kr Ca A1 minus Ks Ca A2. Now, this is my equation number 5, and Rs dCs upon dt Ca A2, that is my equation number 6. Now, sometimes we may need to handle the complex reaction in which both the series and parallel reactions are involved, and sometimes they are designed as a complex reaction to make the product stream more and more perfect in nature. So, we can have this equation or the representation of the complex reaction system like A plus R, that is the K1, and then S may further react with the desired product 1. So, it may gives you this one. So this is one of the way through which you can represent the complex reaction system. Another one is attributed to the independent one. Now these are the reaction that occurred at the same time, but neither the reactant nor product react with themselves or one another. So both the streams are altogether different. Now sometimes mathematically you need to represent all those things for further generation of rate expression and further calculation of optimization of and the performance of those reactions. In that case you can represent like this, that this A is dissociated to form B plus C under the rate constant of K1, and then another thing, that is the D, this may be get dissociated over the period of time to give you E and F. So both the reaction streams, if you see that both the reaction streams are altogether different. Now then we may have to look into the desired and undesired product. Obviously even as an engineer one must have a look into the desired one, and the undesired must be minimized, but unless otherwise we do not have any clue that what are the desired undesired products are being formed in due course of time, then we will not be able to get the optimization when, and we may not be able to get the desired design of those reaction media. So therefore their knowledge, their mathematical representation should be taken into account. So in the multiple reaction usually a reactant can be consumed to form a desired product, which obviously we want to produce, and undesired product obviously we are not looking for or unwanted, but because of the presence of some impurity, because of the presence of some side reaction, because of the some other irreversibility, it may get involved, it may get formed during the course of reaction. In that case we have to write all those things. So you see that here we are having one parallel reaction stream where A is get converted into the desired product R with the rate constant Kr, and undesired product Ks rate constant. Now here you see that here we are having the desired one and undesired one, and unfortunately this R is get dissociated over the period of time to get the to give you the undesired one. So in that case you are having your rate constant with you, so that you can optimize the things accordingly, so that we can improvise the reaction media. Now let us have a look about this. If there is a greater amount of undesired things and as product form, then the larger amount of economy is needed to spend to separate it from the desired product. So your reaction battery or reactor battery would not be economically feasible. So there is a need to minimize the formation of undesired one and fix the reaction condition in such a way that the maximum desired product need to be formed. Now these reaction conditions we can discuss in the later on, because it involves rigorous mathematical approach. Now before we go into these mathematical approach, let us have a look about the qualitative analysis of the product distribution. Now see, this qualitative analysis is again very important or the product distribution, because suppose you are having one product one reactant which is get dissociated over the period of time. One is the desired product stream, another one is the undesired product stream. Under this head you need to have a product distribution profile, because this is giving you R and S both are coming under the head of the product stream. So you must have a proper product distribution profiling, or you have the product profiling system with you, so that you can have a knowledge that how much quantity of the desired product being produced and how much is the undesired one. So this gives you the series and a parallel concept gives you about this particular concept, and in this particular approach when you try to develop the mathematical equation, in that case you must have a knowledge about all the rate constants being involved, whether it is a desired one or the undesired one. Now let us consider into the mathematical approach, like considering the decomposition of a reactant A into the path. Then we are having the desired and undesired one. Now the rate of disappearance of A is the sum of the rate of formation of desired one and undesired one. So in that case minus RA, minus sign is put forward just that A is being disappeared over the period of time during the reaction time. Then this is the RR, that is the rate of desired one, and this one is the rate of undesired one. Now if we introduce the rate constant, then the equation, my equation will become like this. Now the rate equation for the formation of the desired product R, this can be written as like this. Now if we try to write the rate equation for the undesired product, we can represent this equation by Rs is equal to dCs upon dt is equal to Ks upon Ksca A square. So if we divide the rate equation for the desired product with the undesired one, then we may get the relative rate of formation of desired to undesired product, that is sometimes referred as SRS, and this can be represented like this particular equation. Now SRS is equal to RR upon RS, DCR upon DCS, this is the undesired one, and this is equal to KR upon Ks, that is the rate constant Ca A1 minus A2. Now this is the equation number 7. Sometimes, because as an engineering perspective we need to maximize the desired product, so therefore the selectivity parameters, they also play a very vital role, and this SRS should be as large as compared to other one, and my focus should be like this, that it should be as large as possible. So we have to maintain this ratio always greater than 1 to obtain the desired one. Now if we look into this particular equation, then we find that there are several terms which we need to address, like Kr, Ks, they are the reaction rate constant for the desired product and undesired product. A1 and A2, they are the respective orders of the desired reaction and undesired reaction. Now remember, when we talk about the multiple reaction, we need to take care of all these respective orders, whether some one reaction may have the order of 1 and another one may have the order of 2. Then Ca, Cr and Cs, they are the concentration of the reactant A, desired product R and undesired product S. So therefore this in this equation we may have to look into the selectivity parameters. Now Ca is the only factor which can be adjusted and controlled as at a given temperature, when Kr, Ks, A1, A2, they all are constant for a specific system. Therefore, when we look into the desired product, it can be obtained by the controlling the concentration of a reactant A. That means when we talk about this controlling the concentration of reactant A, that means we have zeroed down the things. If you see that the mathematical equation, it consists of a lot of parameters, but and all those parameters, if we consider all those parameters at a time, then definitely my mathematical equation will become so complex in nature, then sometimes the solution won't be easy. So therefore we narrow down the things, and now the things are that we are concentrating towards the reactant A concentration. Now sometimes you need to keep the concentration of A low, so you can use the mixed flow reactor. You can maintain the high conversion. There may be a chance that you may increase the inert in the feed to or decrease the pressure in the gas phase system if you are handling that gas phase system in this one. Now if you wish to keep the concentration of A on the higher side, then you may use the batch or a plug flow reactor. We have discussed the protocol of all these three reactors in the previous lecture: batch reactor, plug flow reactor, mixed flow reactor, etc. You may maintain the low concentration. You may remove the inert from the feed, or you can stop the insertion of all inert to the feed. You may increase the pressure in the gas phase system. Now there are various cases by which we can control the formation of a desired and undesired product. One approach is that you can write this mathematical equation, or we are having this mathematical equation with us, that is SRS is equal to RR upon RS and DCR upon DCS, or equal to KR SCA A1 minus A2. Now if we consider the first case, when we may have A1 is greater than A2. that is the desired reaction order is higher than the undesired one. That is obviously, as an engineering perspective, it is more favorable condition. So, in that case, keep the concentration of reactant as high as possible. Now, it keep the ratio high, this ratio on the higher side, and favor the desired product formation. Now, sometimes the use of a batch or a plug flow reactor is always preferred to have in the minimum size, because the concentration of the reactant sometimes drop progressively during the course of a reaction in the reactor mass. So, but sometimes you may not use the mixed flow reactor, as the concentration of reactant is always at its lowest value, that of the outlet concentration. Now, another case, when the A1 is less than A2, that means the desired reaction order is of lower order compared to the undesired one. Now, here we need to keep the low concentration to favor the formation of a desired product. Now, you need to keep the selectivity parameter ratio as high as possible. You may require the larger mix flow rate, and you may require the dilution in the feed stream. Now, the last case is that in which we can have this A1 is equal to A2, that is the desired reaction order is of the same order as the undesired one. Now, here the product distribution is usually fixed by Kr upon Ks ratio, and unaffected by the type of reactor being used. So, let us have a brief look about this, the mathematical approach. Now, the desired for the case 3. Now, here Rr upon Rs, that is equal to Dcr upon Dcs, that is equal to Kr upon Ks, that should be constant. Now, we may control the product distribution too by varying the ratio of a specific rate constant for desired and unwanted reaction, and sometimes referred as Kr/Ks ratio. Now, there are a couple of cases through which we can address this particular issue by changing the temperature level of the system. Sometimes the activation energy, it play a very vital role. So, activation energy of two reactions, they are different and unknown, the ratio, that is the Kr upon Ks. So, in that case, we can write the things like controlling the product parameters, like we can write Kr upon Ks, that is K Ro e to the power minus E upon R T, that is E R small r, divided by Ks naught e to the power minus Es upon R T. Similarly, Kr upon Ks is equal to Kr Ks naught e to the power minus Er minus Es upon RT. So, this is my desired equation. Now, this ratio Kr upon Ks changes with the temperature, and usually depends on whether the activation energy is greater or smaller than Es. So, if the activation energy of the desired product is greater or smaller than the activation energy of undesired product. Now, when temperature rises, in that case the Kr over Ks ratio increases, and in that case the activation energy of the desired one will be greater than activation energy of undesired one. Now, if in that case the Kr upon Ks ratio decreases, in that case the activation energy of the desired product will be less than the undesired one. So, higher temperature usually favors the reaction of higher activation energy, and lower temperature usually favor the reaction of lower activation energy. Now, sometimes we may use the case 2 by using the catalyst, although it is a very common phenomena in the industrial approaches. Now, one of the most important feature of a catalyst, that is the selectivity in the pressing or deaccelerating the specific reaction. Sometimes this may be much more effective way of controlling the product distribution than any of the method which we discussed. So, for parallel reaction system, the reactant concentration is usually the key to control the product distribution, and a high concentration of reactant usually favors the reaction of higher order, and a low concentration favors the reaction of a lower order. So, while concentration level has no effect on the product distribution if reactions are of the same order. Now, in this particular segment, we discussed the various concepts attributed to the product distribution, the concepts attributed to the selectivity, concept related to the various permutation and combination of different type of reaction mechanism maybe with, and we discussed all these things under the head of various cases. So, in case if you wish to have further study, we have enlisted couple of references for convenience. Thank you very much.